Welcome back to the 8th lecture of Open Course on Diffusion in Multi-Component Solids. In this lecture, we will go over the statistical model for evaluating the enthalpy of mixing for a regular solution, and again to give a flavor of multi-component thermodynamics, I have treated ternary solution in this lecture. So, last class we analyzed ideal solutions. Today we will try to analyze Gibbs free energy of mixing for non-ideal solutions. So, delta Gm is equal to delta Hm minus T delta Sm. Unlike an ideal solution, for a non-ideal solution, delta H mixing is not 0, right? It has a non-zero value. So, heat is either evolved or heat is absorbed during the process of mixing. Why it would happen? Because of the interactions, because AA, BB and AB interactions are different, and when we replace some of the AA and BB pairs with AB pairs in the solution, there is a heat effect. The potential energy changes, so the enthalpy changes. Now, when this is so, when AA, BB and AB interactions are not same, then in real solutions the mixing will not be random, right, because there will be some preference for the nearest neighbor pairs. For example, if AB bonds are stronger than AA and BB bonds, then there will be a tendency to form, or there will be a tendency to maximize AB bonds. On the other hand, if AB bonds are weaker, there will be a tendency to form AA and BB bonds and minimize the number of AB bonds, right. So, there will be a kind of short range order associated with the difference in the interactions, and so the mixing process will not be completely random, and so delta S mixing will not be same as that for an ideal mixing where we assume random mixing, right. But in order to understand this interaction effect, let us try to simplify the model. Okay. So, let us assume that delta Hm is not 0, still delta Sm is equal to delta Sm id. So, this is the regular solution model. So, now we need to evaluate the enthalpy of mixing. You know, delta Hm at constant temperature and pressure, you can write this as delta U plus P delta V we make further assumption that delta V is negligible, and so delta Hm just becomes equal to change in internal energy. Further, temperature is constant, so we do not need to consider the changes in kinetic energy. So, delta Hm is equal to delta Em, where E denotes the potential energy part, and the change in potential energy is only because of the changes in the types of pairs or changes in the number of particular bonds AA, BB or AB in a binary solution. Okay. So, let us try to evaluate this, and let us consider a ternary solution. For example, we are considering 1 mole of solution formed by mixing of in in 1 atoms of 1, in 2 atoms of 2, and in 3 atoms of 3. So, let us denote their potential energy before mixing as E1, and potential energy after mixing as E2. Now, if we consider the solution after mixing, how many different types of bonds will be there? Oh no, we are considering ternary solution. There will be of course 1 1. So, the types of bonds we are considering will be 1 1, 2 2, 3 3. Then there will also be dissimilar atom interactions, so or bonds. So, it will be 1 2, 1 3, 2 3, right. So, there will be 6 types of bonds. Let us say there are P11 number of 1 1 type of bonds, and each bond has an energy E11. Similarly, P22 number of bonds, each having energy E22. P3 number of 3 3 bonds, each having energy E33. P12 bonds with energy E12 per bond, P13 bonds with energy E13, and P23 bonds with energy E23. So, what will be the total energy after mixing? Yeah. We take a particular bond, multiply by energy per bond. So, we have P11 times E11 plus P22 times E22 plus P33 times E33 plus P12 times E12 plus P13 times E13 plus P23 times E23. And what will be the energy before mixing? Before mixing, there will be no dissimilar bonds, right. So, only 1 1 2 2 and 3 3 bonds, and their numbers will be obviously different. So, let us assume they are P11 prime, P22 prime and P33 prime. In that case, total potential energy before mixing will be P11 prime E11 plus P22 prime E22 plus P33 prime E33. And so, delta EM we can write as E2 minus E1, that will be P11 minus P11 prime times E11 plus P22 minus P22 prime times E22 plus P33 minus P33 prime times E33 plus the terms related to dissimilar bonds, P12 times E12 plus P13 times E13 plus P23 times E23. So, now all we need to do is to evaluate this number of bonds. So, to do that let us apply a balance equation for number of bonds. So, if we try to find the total number of bonds, and if we write as total number of atoms of type 1 times number of bonds per atom. So, if we consider total number of 1 atoms multiplied by number of bonds per atom. So, how many types of bonds atoms of types 1 will be involved in? They will be either 1-1 or 1-2 or 1-3, right. So, if we do this for 1-1 type of bond, then essentially we are counting it twice, right. So, 1 for this 1 atom, again this bond is counted during the second 1 atom. So, this has to be 2 times P11, and for the dissimilar type of bonds we are counting only once. So, that should be equal to P12 plus P13, and if the left hand side, if we see total number of 1 atoms is N1 and the number of bonds per atom should be equal to the coordination number, let us call it Z, and so we can get P11 is basically 1/2 N1Z minus 1/2 P12 minus 1/2 P13. Similarly, we can apply this for atoms of type 2 and also atoms of type 3, and we will get P22 is equal to 1/2 N2Z minus number of dissimilar bonds in which 2 is involved, 1/2 P12 minus 1/2 P23, and P33 should be equal to 1/2 N3Z minus 1/2 P13 minus 1/2 P23. Now, if we apply this equation before mixing, where we essentially have pure 1, pure 2 and pure 3, right. So, before mixing, if we consider element 1, that will be essentially, this will remain same, N1 times Z should be equal to 2 times P11 prime, because there are no dissimilar bonds, and so P11 prime is essentially 1/2 N1Z. Similarly, P22 prime will be 1/2 N2Z, and P33 prime should be 1/2 N3Z. So, now if you substitute for P11 and P11 prime in this equation, you can find delta EM P11 minus P11 prime. So, these terms will get cancelled, 1/2 N1Z, 1/2 N2Z and 1/2 N3Z. So, you get essentially minus half P12 E11 minus half P13 E11 half P12 E22 minus half P23 E22 minus half P13 E33 minus half P23 E33 plus this term will be P12 E12 plus P13 E13 plus P23 E23. If we rearrange, so essentially what we have found, delta Hm, this is equal to delta Hm. Yeah.
Sir, how can we assume that the coordination number for all the three type of atoms can be same?
Okay, so that is a good question. So there is an assumption that we are making here. We are starting with same crystal structure as the crystal structure of the solution, right. That is how we systematically form a thermodynamic solution. For example, in a binary, if we want to form a solution between A and B, which is FCC, right, we first bring pure A to FCC structure, we bring pure B to FCC structure, and then mix the two to form the final FCC solution. Okay, so if A and B are stable as FCC, then we just have to consider A and B in stable phases. But suppose B is not stable as FCC, B is stable as HCP, so we first have to convert HCP to FCC. There will be some Gibbs free energy change associated with it, and then we mix the two to form the final solution, which is FCC. Okay, so that is the assumption. Good question, and that is why we are considering the coordination number is the same. So we rearrange this, what we get is, if we take the terms related to so P12 E12, so we have P12 P12 and P12 times E12 minus E11 plus E22 by 2, similarly plus P13 times E13 minus E11 plus E33 by 2 plus P23 times E23 minus E22 plus E33 divided by 2. Okay, so essentially we are multiplying the number of dissimilar bonds with the difference between the energy of that dissimilar bond and the average of the similar type of bonds. Right. So if we write this for binary, for example, this will be delta Hm is equal to, we are considering AB solution, then PAB times EAB minus EAA plus EBB by 2, and this will be 0 if EAB is equal to average of AA and BB bond energy, right. If EAB is equal to EAA plus EBB by 2, delta H mixing is 0, and then it is an ideal solution, right. So for a solution to be an ideal solution, what we initially said is the interactions have to be same, but it can be little more relaxed as long as the AB bond energy is equal to the average of AA and BB bond energies, we can still get an ideal solution. If we have a ternary solution, then that has to be true for each of the dissimilar pair, then solution is an ideal solution. Even if for one of the pair that is not true, then you will have some non-zero value of delta Hm and the solution will be non-ideal. Okay. So, now to look into this further, we need to evaluate Pij's, where I and J are different types of atoms. So, P12, P13, P23 for ternary. So, how do we evaluate Pij? Number of Ij pairs. If we know the total number of pairs and multiply it by the probability that a particular pair is an Ij pair, we will get Pij. So, Pij is equal to total number of atom pairs multiplied by that probability that a given pair is an Ij pair. So, this first term will be how many total number of atom pairs will be there? This will be simply NaZ by 2, right, total number of atoms times number of bonds per atom, and since we are counting each bond twice, so we divide by 2. What will be this? So, if we have a crystal structure with given number of atom pairs, so what is the probability that a selected pair, let us say this one, is an Ij pair? So, how we select the pair? We select the first atom and then the next nearest neighbor, right. So, what is the probability that the first atom is an I atom? If we consider random solution, which we are considering here, right, then the probability that a selected atom is nothing but the mole fraction of that atom, right, multiplied by the probability that the next atom is an J atom, which is Xj. This will be Xi times Xj, or we can select first atom to be a J atom and the next one to be an I atom. In that case, it will be Xj Xi. Right. So, this will be Xi Xj plus Xj Xi. So, this will be basically 2 Xi Xj, and so Pij becomes NaZ Xi Xj. So, we substitute there for ternary, we get delta Hm is equal to NaZ times E12 minus E11 plus E22 by 2 times x1 x2 plus NaZ time E13 minus E11 plus E33 by 2 times x1 x3 plus NaZ times E23 minus E22 plus E33 by 2 times x2 x3. If we denote this term as omega ij, then we have delta Hm is equal to omega 1 2 x1 x2 plus omega 1 3 x1 x3 plus omega 2 3 x2 x3, where omega ij is nothing but NAZ Eij minus Eii plus Ejj divided by 2. Clear? So, we have the expression for molar enthalpy of mixing in terms of bond energies of different types in the solution. So, if we consider the binary solution, then delta H mixing in that case will be should be equal to omega AB XA XB. Since there is only one term omega, we can just call it omega, where omega is equal to NAZ times EAB minus EAA plus EBB by 2. Now, when AB bond energy, as we have seen, is same as or is equal to the average of AA and BB bond energies, then delta Hm is 0 and the solution is ideal. But when EAB is less than average of AA and BB bond energies, omega is less than 0, which means delta Hm is less than 0. So, essentially what this means is, if AB bonds are stronger, the stronger bonds means lesser bond energy, right. So, when AB bonds are stronger than average of AA and BB bonds, then the enthalpy of mixing is negative, which means heat will be released during the process of mixing. We have seen when we studied the Raoult's law and the Henry's law, or how the vapor pressures vary with composition, that we studied, right. So, that time if you remember, if AB bonds are stronger than AA or BB bonds, we said that the evaporation rate or the intrinsic evaporation rate of A will come down by going into the solution from pure state, right. That corresponded to the negative deviation from ideality. So, here it means that negative deviation of ideality also means that delta H mixing is negative. Similarly, if AB bonds are stronger than AA or BB, which means in this case if EAB is greater than average of AA and BB bond energies, then omega is greater than 0 and delta H mixing is greater than 0, which means heat will be absorbed during the process of mixing. This physically you can, it is obvious, right, you can see it. If AB bonds are weaker, which means AB bonds have higher energy than average of AA and BB, and by forming solution you are replacing some AA and some BB bonds with AB bonds. So, you are replacing stronger bonds with weaker bonds, you are replacing bonds with lower energy with bonds with higher energy, which means energy has to be provided to form the solution, right, and that is why delta H will be positive. Okay. So, this is important. We went over this model in little bit details because it is important to understand how the interactions between the atoms give rise to the changes in the Gibbs free energy, basically changes in the enthalpies and entropies, because they also affect the diffusion, especially the cross effects, right. Because of these different interactions, the atom jumps will be biased in a multi component system, and so it is important to understand this, how these atom interactions affect the Gibbs free energy changes. So, now if we plot for an AB solution, so for a regular solution, delta GM regular, you can write it as delta HM regular minus T delta SM ID. Delta HM regular, we are now talking of binary AB solution. We know this will be omega XA XB plus RT XA ln XA plus XB ln XB. Now, if we try to plot delta HM, delta SM and delta GM, when let us say omega is less than 0, when omega is less than 0, delta HM will be negative, right. So, omega XA XB has a shape something like this. So, this is delta HM. Delta SM regular is same as delta SM ID. So, we know it has a shape, it will be positive always, and so if we evaluate delta GM at each of the composition, it will be negative everywhere. So, this is delta SM, this is delta GM, this is XP. What if omega is positive? Delta SM will still be positive everywhere. Now, delta HM is positive, and so delta GM, you will see the magnitudes of delta GM would be lesser than what it would be for negative omega. So, as this becomes more and more positive, what happens? This curve will increasing. It will also affect the curvature of delta GM, right. And when delta HM is very high, you will see there will be a negative curvature developed on the delta GM curve. So, this delta GM curve corresponds to this delta HM. We are still assuming ideal or random mixing. So, delta SM will not change for assumption of random mixing, but then because delta HM is becoming more and more positive, it will affect the curvature, and at beyond certain value of delta HM it will just develop a negative curvature in between. Now, this is very important because it will affect the stability of the solution. okay, and how it will affect we will see in the next class. Any questions so far? It's all clear? Okay, thank you.